Today, we're breaking down the incredible science behind some of humanity's most powerful creations. We're talking about everything from machines that can literally forge lightning right here on Earth, to the vehicles that somehow survive a fiery, blazing return from space. So let's just dive right in with a huge question. How in the world do you create a force strong enough to defy gravity itself, but without using a single drop of rocket fuel? I know, it sounds like something straight out of science fiction, right? But the answer lies in a fundamental force of the universe that we've actually learned to harness. And to get to that answer, we need to talk about a force you can't see, you can't touch, but it underpins pretty much everything in our modern world. I mean, from simple electric motors to absolutely massive particle accelerators, it's all about the invisible power of electromagnetism. And the secret sauce here is something called the Lorentz force. It's really the fundamental rule for how electricity and magnetism play together. Put simply, when you have an electric charge moving through a magnetic field, that field pushes on it. It creates a force. And if you can master that interaction, well, you can create some truly incredible motion. The entire beautiful concept boils down to this one simple equation. The force, F, equals the charge, Q, times its velocity, V, as it's moving through a magnetic field, B. And it's such an elegant relationship when you think about it. The more charge you have, or the faster it's moving, or the stronger the magnetic field, the more force you get. This right here, this is the recipe for everything we're about to see. So what happens when engineers take that elegant little equation and just push it to its absolute breaking point limit? Well, you get machines that generate forces and speeds that are almost beyond human comprehension. Okay, check this thing out. This is a flux compression generator, and its principle is, well, it's brutally effective. You literally detonate high explosives all around a metal cylinder to instantly, violently crush it, and any magnetic field that's trapped inside has nowhere to go, so it gets squeezed, compressed into this unbelievably dense state. And the result of that controlled, violent squeeze, a magnetic pulse that can reach up to 133 Tesla. Now, to put that number in perspective for you, that's millions of times stronger than the magnetic field of our entire planet. It's like creating a momentary, man-made magnetic star, just so scientists can study how materials behave under conditions that, frankly, don't exist anywhere else on Earth. Okay, so that's how you make a massive, instantaneous magnetic pulse. But what if you want to use that same Lorentz force for sustained motion? For propulsion? Well, that's where the electromagnetic railgun comes in. So instead of explosives, a railgun uses a monster pulse of electricity. It flows down one rail, cuts across a conductive projectile, they call it an armature, and then goes back up the other rail. This whole circuit creates an absolutely intense magnetic field that shoves that armature forward with immense force, accelerating it to just unbelievable speeds. So let's just step back for a second. We have two totally amazing machines, both built on the exact same physics principle. On one side, you've got the generator, using an explosion to create this brief, staggering magnetic field for pure research. And on the other, you have the railgun, using electricity to create sustained, mind-boggling acceleration. Same physics, totally different outcomes. All right, now let's zoom way out. We've been talking about creating immense forces here on Earth. Let's talk about managing those forces on a truly cosmic scale. And that brings us to the ultimate challenge: escaping Earth's gravity, and maybe even more important, surviving the trip back home. Here's the fundamental problem with re-entry. A spacecraft that's in orbit has a colossal amount of energy, both kinetic and potential. And to land safely, all of that energy has to go somewhere. It gets dissipated, mostly as heat, as that vehicle slams into the atmosphere at over 17,000 miles an hour. When a vehicle like the Space Shuttle comes back to Earth, it's performing this delicate, high-stakes ballet with physics. You can see all the forces at play here. Gravity's pulling it down, lift is affecting its path, but the real star of the show, the force you're desperately counting on, is atmospheric drag. It's the friction that's going to slow you down. And that delicate balance creates what pilots call the re-entry corridor. And trust me, it is razor thin. If you come in too steep, the drag is so intense that you just burn up. But if you come in too shallow, the atmosphere acts like the surface of a lake. You'll literally skip right off of it and bounce back out into space. And this is what hitting that atmospheric wall feels like. Just look at this graph. The faster you come in, the more crushing the g-forces of deceleration become. we're talking about a vehicle experiencing nearly 200 Gs. I mean, just surviving that is a monumental engineering challenge. So the big question is, how do you possibly survive this fiery plunge? Well, engineers have come up with 3 really clever means strategies. You can use a heat sink, which basically acts like a giant sponge to just absorb all that heat. You can use an ablative shield that literally burns away, carrying the heat away with it. Or you can do what the space shuttle did and use special tiles that get white hot and just radiate all that heat back out into space. Okay, so dealing with the extreme forces and the physics is one thing. But with stakes this high, we're talking life and death, managing the risk is a whole other ballgame. So how do you do that? You write rules. Lots and lots of very, very specific rules. And to show you just how serious this gets, let's look at a term from the Japan Aerospace Exploration Agency's safety manual, a hangfire. Just try to imagine this for a second. You have a fully fueled rocket, the engines have ignited, they're roaring, the ground is shaking, but the rocket isn't moving. It's just sitting there on the launch pad. It is one of the most dangerous situations you can possibly imagine. So what do? Well, you follow the procedure. And this is not just some boring checklist, folks. This is a life or death protocol, a carefully choreographed dance that's been perfected over decades. You make sure the flight termination system is armed. You wait a full 30 minutes for safety. You check for any stray signals. And only then do you even think about approaching that live rocket. But you know, the risk isn't just about the folks on the launch pad. The regulators have an even bigger job, protecting the public from anything that might go wrong once that rocket is in the air. And to do that, you have to do something that sounds almost impossible. You have to put a number on risk. Here in the United States, the FAA sets a very, very hard limit. For every single launch, they calculate a number called expected casualty. And the rule could not be simpler. The probability of a casualty has to be less than 30 in a million. If the math says the risk is any higher than that, the launch does not get approved. Period. No negotiation, no exceptions. It's a hard stop. And this isn't just an American thing. This kind of super rigorous approach to safety is global. Space agencies all over the world have these systematic risk management plans. They try to identify every conceivable thing that could go wrong, analyze it, and figure out a way to mitigate it, literally building safety into the very fabric of space exploration. And that really brings our whole journey full circle, doesn't it? We started with one tiny, elegant principle of physics. We saw how you can scale it up to build these extreme machines, how it defines the life or death challenges of coming home from space, and finally, how it all leads to this global framework of rules designed to manage that immense power safely. You see, this mastery of force, from the tiniest particles to the cosmic scale, it's not really an endpoint. It's the foundation. It's the toolkit for whatever we decide to build next. So the real question isn't whether we can harness these incredible forces anymore. The question is, what are we going to do with it? Where do we choose to go from here?